Hello, welcome to MAT 223 Engineering Mathematics class. In this lecture, we will talk about differential equations as mathematical models. Since its first existence, mathematics has been employed to measure quantities of products. For example, a farmer counts their tomatoes, or a shepherd counts their, for example, sheep. As of today, its usage extended to simulate physical life phenomena. This is not only the just one option, but the it's where mathematics is going. So, for instance, global warming, the spread of COVID-19 disease, heat transfer, trajectories of Elon Musk's rockets, etc. is among all these research subjects of mathematical modeling and simulation. These hot topics are currently under investigation by researchers. Also, some mathematical models are well investigated already and formulated with some basic assumptions. Their formulations are commonly accepted by the community for their primitive purposes. One of the purposes is also education. We teach how to model with using differential equations with these assumptions and with these primitive equations. In this lecture, we will cover some of those. The first one is uninhibited growth. The second will be exponential decay. The first and second is pretty much the same. They will lead the same differential equation except with a minus sign in front. And the next one will be Newton's law of cooling. And the last one will be mixing problems. First, if we start with the algorithm for modeling, first we start with an assumption or hypothesis for the real life or physical problem. Then we use these assumptions and hypotheses to come up with a mathematical model, and then we solve this mathematical model and find solutions. Once we have solutions, we compare our solutions with physical expectations, and then if we find the solutions are meeting with our expectations, then we say, okay, this is a good modeling, and then we break the circle and we say, okay, we can use this model. But if not, if it doesn't work, then we say, okay, keep going, change our assumptions, and then change the mathematical model based on these new assumptions, and then these new assumptions will lead new mathematical model. New models will give us new solutions, and new solutions will give us new opportunities to check with our physical expectations. If we are done with these physical expectations, then we will use this mathematical model. Otherwise, we will follow the circle again and again until we are satisfied with the solutions. Okay, so this is the cycle for coming up with a mathematical model. The first mathematical model will be uninhibited growth or exponential decay. The assumption for this particular model will be that there is a hypothesis that some bacteria culture obey the law of uninhibited growth. What is that so? The rate at which the population is growing is proportional to the number of individuals. Okay, so mathematical model is to come up with a mathematical model. Let's define the number of bacteria first. PT is the number of bacteria. The number of bacteria, the number of individuals in the culture is time dependent. It's a dynamical system. Time dependent systems are dynamical systems. And if it is not time dependent, then we say static model. Okay, so it is dynamical in this case, and the number of individuals is a function of time t. So we define pt to be the number of bacteria. Okay, next, since the rate of change means derivative, we conclude that dp dt, the time derivative of number of individuals, is equal to the rate at which the population is growing. Okay, So the derivative will be the rate of change in the population growth. Okay, the assumption of the model dictates that dp dt is proportional to pt. This is proportional sign. dp dt is proportional to pt. Then we say, okay, proportionality means there is a constant lambda, so that dp dt is equal to lambda times pt. Okay, so this is our differential equation for based on our assumption. Okay, since this is a growth model, we expect dp dt to be a positive number, right? Because if it is growth model, then the function has to be increasing. Increasing means the derivative positive. So the left hand side is positive. On the right hand side, we have number of individuals. So P, it's a number of the bacteria. So it cannot be negative. Okay, so it's positive. So positive, positive. As a result, lambda has to be positive. Okay. Now, let's see this phenomenon on an example. A culture of 2000 bacteria grows according to the law of uninhibited growth. If there are 2200 bacteria after an hour, how much bacteria in the culture after 8 hours? Okay, let's say Pt be the number of bacteria at time t. Also, we know P0 is equal to 2000 because there are 2000 bacteria initially. By the law of uninhibited growth, we construct the following differential equation for some proportionality constant lambda. Okay, dp dt is equal to lambda times pt, and p0 equals 2000. We can solve this differential equation by separation of parameters and find pt is equal to p0 times e to the lambda t. I skip this part since I don't do the separation of parameters and solve this problem. It's basic enough. You can do that on your own. Actually, you should do that on your own and see really if you get the same results with me. Okay, so this is the solution. And then if we consider the initial condition, if you substitute 0 for t, this will be basically 1. P0 will be then 2000. Okay, so our solution will be pt is equal to 2000 times e to the lambda t. Okay, so this is the model, and we solve the problem and get the solution. For any given time, we can find the number of bacteria using this solution. Okay, but we have a problem at this point now because for example, here we don't have any ideas about what the lambda value is. Okay, so we need to find it. To that end, we have to use some other information given in the problem. This problem is here. This information is here. If there are 2200 bacteria after an hour, okay, so this means P1 is equal to 2200. Okay, so P1 has to be 2200. If we substitute 1 for T, we expect PT to be 2200. Okay, let's do that. P1 is equal to 2000 times e to the lambda times 1 equals 2200. Then if we solve this for lambda, we'll see lambda is equal to natural log of 2200 over 2000. Okay, and if we use our calculator, we'll see this number is approximately equal to 0.09531. Okay, now we have the solution. Okay, at this point indeed we can find find the number of individuals, about number of bacteria for any given time. Okay, so now if you return to the question, it asks us about how much bacteria in the culture after 8 hours. Okay, so it means we substitute 8 for t and find the number of individuals, number of bacteria. And if we substitute 8 for t, we will end up with 2000 times e to the lambda times 8, and this will be 4287.17. Okay, and this is a number of bacteria, so this cannot be a decimal number, so we will eliminate this part and we'll say 4287 bacteria will exist in the culture after 8 hours. Okay, so this is pretty nice because we solve differential equations and then we get the number of bacteria after some time. Okay, next we will talk about exponential decay. The assumption is about radioactive decay now. So according to the radioactive decay law, the rate at which the amount of radioactive material is decreasing this time, is proportional to the amount of material itself. Okay, so basically, as you see, the amount is proportional to the rate of change at this time. Okay, so it's pretty much the same with the previous one, but except with a sign. Okay, so AT, say AT is the amount of the radioactive material, and dAdt is the rate of change, rate at which the amount of radioactive material is decreasing this time. It was increasing before, decreasing this time, and then we say the assumption dictates we have dAdt proportional to AT, and then this will be basically equal to dAdt is equal to some constant times AT. Why we have negative here? So it can be positive as well, but we just want to make lambda positive. That's why we put negative here and try to show this is really a decay problem. So it's really a modeling a decrease process. So let's check the signs for if we consider the derivative. Okay, so the derivative has to be negative because it's a decay model, so this derivative has to be negative, right? Because we have decreasing amount. Okay, so this is negative, and AT is the amount. It cannot be negative, so it's positive. A lambda is positive, then we have to have some negative number here to make sure we model a decreasing process. Okay, so this is a decay model, so we have lambda is positive and we have negative sign here to make sure people understand this is really a decreasing model. Okay, so the example will be the initial mass of an iodine isotope was 200 grams. Determine the iodine mass after 30 days if the half-life of the isotope is 8 days. Okay, so this is a given information and this is initial amount, and we know this is radioactive decay, so we use the assumption for radioactive decay law, and then we also use the initial amount here, and also we use the half-life of the isotope, and this is also an extra information to find the constant lambda. Okay, and then the question asks about finding the amount of the iodine after 30 days. Okay, so this is what the problem really says. Okay, if we say AT be the mass of iodine, and this is still dynamic system because it's the amount of iodine is changing depending on time. Okay, so say AT is the mass of iodine at time t. Also, we know A0 is equal to 200. It's given. Initially, we have 200 grams of iodine. By the radioactive decay law, we constructed the differential equation like this. So this is an initial value problem. Okay, so this is from the assumption the rate of change in the amount is proportional to the amount itself. So it is basically this model. Okay, we solve this differential equation and find AT is equal to some constant A naught times e to the negative lambda t. Okay, and then we use the initial condition. We substitute 0 for t, and we see this is just 1, and then A naught will be 200. Okay, so this will be the solution for our initial value problem. Okay, then we need to find lambda. to that end, we need to use this information given here. If the half-life of the isotope is 8 days, okay, half-life means after 8 days, our amount will be the half of what was existed in the beginning. Okay, so in the beginning we have 200 grams, and then A8 has to be 100. Okay, so after 8 days we'll have the half of the amount, half of the initial amount, so this will be 100. Okay, so if we use this information and substitute 8 for T and 100 for AT, then we will have A8 is equal to 200 times e to negative lambda times 8, and this is equal to 100, and then lambda will be equal to negative 1/8 ln 100 over 200, and this will be equal to ln 2 over 8. Okay, so now we can substitute this lambda value in the equation here, in this equation here, and then we see the lambda value will be, let's remove this. Okay, then if we substitute the lambda value there, we will see this is our solution. Okay, so for any given time t, we can find the amount of iodine. Okay, so it asks us about finding the amount of iodine after 30 days. So it's basically A of 30. Okay, so A of 30 is equal to the value of the right hand side at t equals 30. So if we substitute t equals 30 on the right hand side, we see 200 times e to the negative lambda times 30, and this will be basically approximately equal to 14.9 grams. Okay, so this is our solution. Next, we will talk about Newton's law of cooling. The assumption for that will be, according to Newton's law of cooling, the rate at which the temperature of an object is changing is proportional to the difference between its temperature and the temperature of its surrounding. Okay, so for the mathematical model, let's start with defining some functions like T of T is the temperature of the object, and then we say dt is basically the rate at which the temperature of the object is changing, and then our assumption for the model dictates that dt, the rate of change in the temperature, is proportional to the difference between the surrounding temperature minus the temperature of the object. Okay, so this is the temperature difference between the object and its surrounding environment. Okay, then this basically means dt is equal to some constant times Ts, the temperature of its temperature of environment, minus the temperature of object, and K is some proportionality constant. Okay, here there are some explanation for the sign of this K number. Okay, so let's go back to the equation again and discuss it here. If we say the object is hotter than the surrounding environment, if its temperature is more than surrounding environment, then we see the surrounding environment minus the temperature of object will be, this part will be negative number. Okay, and this is a negative number and K is positive. Okay, this is negative and K is positive. Then we see negative times positive will be a negative number here. Then dt has to be negative. So this means temperature of the object is decreasing. Is it really the case? The answer is yes, because if the temperature of the object is higher than the temperature of environment, then its temperature has to decrease, right? This is what we really expect. Okay, if you see the other way around, if the temperature of the surrounding is higher than the temperature of the object, then this will be a positive number, and k is positive, then we have positive number on the right hand side, so the derivative is positive. This means the temperature of the object is increasing. This is really the case because the temperature of surrounding is higher than the temperature of object, so the object will gain some heat and its temperature will increase. Okay, so if we solve this differential equation using separation of variables, like here, as you see, we don't have any t here, right, on the right hand side. This is just a function of t, capital T. So we can solve this by separation of parameters, and when we do that, we get this solution. Okay, so you need to read through the notes and understand why this is really happening and solve this problem on your own. Okay, so this will be our solution. An example: miners have to cool a mining kit by fully sinking it in a water tank located by their side every time before reusing it. This water tank has a constant temperature of 5 degrees Celsius, and the kit's temperature after each use is 100 degrees Celsius. Okay, so then they observe that this kit's temperature reduces to 60 degrees Celsius after 10 seconds of sinking in water. Okay, being a mining engineer candidate, find the temperature of the kit as a function of time. Okay, so let Tt be the temperature of the kit at time t. Okay, also we know T0 is equal to 100 because after each use its temperature will be 100 here. Okay, it's given, and then we know after 10 seconds the temperature of the kits will reduce to 60 degrees Celsius, so it is T of 10 is equal to 60 degrees Celsius. Okay, these are all given. By Newton's law of cooling, we construct the following differential equation. Okay, so dt is equal to k times the temperature of surrounding environment. So in this case it is the water in the tank. Okay, so it is 5 degrees of Celsius. Okay, so this is 5 minus the temperature of the kit. Okay, times some k is equal to dt. Okay, and also we know initially we have 100 degree for the object, so this will be an initial value problem. Okay, we can solve this differential equation by separation of parameters and find this solution. Okay, this can be solved by separation of variables easily. This is basically dt over 5 minus t is equal to k times dt, and here we will have natural log and we will have a kt on the right hand side, and then if we take the natural log, if we eliminate natural log, we will end up with the exponential function and it will look like this. Okay, you should do it on your own. Okay, and then if we use the initial condition and substitute 0 for time t, then we'll end up with this will be just 1 and c will be here, only c will remain from that term, and we will have 5 plus c is equal to 100 and c will be equal to 95. Okay, so this will be our solution. Okay, now we are almost there, but except one unknown. K is still not known, right? So we need to find k, just like we did for lambda. Okay, so for this k value we need to use extra information given here. Okay, so it is T of 10 is equal to 600. Okay, this means if we substitute 10 for t time t, then the temperature will be 60. Okay, so if we do that, next to find k, substitute t of 10 is equal to 60, then t of 10 is equal to 5 plus 95 e to the negative k times 10 equals 60, and then this will be 55 over 95 divided by, actually we take the natural log and divide by negative 1 over 10, In this case, we will end up with this quantity. Okay, so this is our key. Now if we substitute this in the equation we found, we see T of t is equal to 5 plus 95 e to the negative 0.054t. Okay, so this is our solution, and we already had to find some function for the temperature of kits, right? This was find the temperature of the kit as a function of time, so we already found it. So the problem is solved already by at this point. Okay, also we observed that if we let the time go to infinity, okay, so if we let the time goes to infinity, I mean if we extend the time, if we put the kit in the water and wait really long, then what happens to the temperature of kit? it this means basically we need to take this limit and see what's really happening. As t approaches infinity, t is equal to t approaching infinity limit 5 plus 95 e to the negative something t, and we know as t approaches infinity, e to the negative infinity will be basically 0. Okay, so this will approach to 0, and this part will go away because this is basically 0, and then if this goes away we end up with 5. Okay, so this means if we sink the kit in the water and wait long enough, we'll see its temperature will approach to the temperature of water, and this is what really we expect from the physics perspective of the problem. Okay, so this makes sense. Next we will talk about mixing problems. Let a holding tank be filled by a liquid solution of a substance. Also let the liquid will be entering, an extra liquid will be entering and leaving this holding tank. Okay, liquid entering the tank may be a solution of less or more substance. Okay, liquid leaving the tank is also a solution of this substance, because there is a solution of this substance in the tank, and if something leaving from the tank, this has to be the solution of this substance. Okay, and we also assume this substance, the tank is well stirred, and as soon as something leaves or something enters, it will be homogeneous. Okay, it will be well mixed. Okay, in this particular setting our goal is to find the amount of substance in the tank for a given time t. Okay, first define qt to be the amount of substance in the tank. Okay, q in amount of the substance entering the tank, and q out is the amount of the substance leaving the tank. These are all at time t, and q0 is the amount of substance initially in the tank. Okay, so this is the initial amount and this is not time dependent. Okay, the conservation of mass requires the following equality, right? Qt, the amount of the substance in the tank, is equal to the initial amount plus entering amount minus leaving amount. Okay, so this is basically the conservation of mass. Okay, if we take the time derivative, on this equation, we'll see dq dt is equal to, basically this time derivative of this function will be this number will be basically 0 because it's not time dependent, right? It's like 200 gram, for example, or 1,000 kilogram, for example. Okay, so this is something we can eliminate after taking derivative. Okay, so dq dt will be equal to dq in dt minus dq out dt. Okay, so this basically means the rate of change of the substance in the tank is equal to the entering rate minus leaving rate. Rate of entering amount minus rate of leaving amount. Okay, so we will use this basic equation to construct our mixing problems. Okay, mixing models. Okay, a holding tank initially contains 40 kg of salt dissolved in 600 liters of water. A solution containing 0.5 kg of salt per liter starts to pour into the tank at the rate of 4 liters per minute, and well-stirred mixture is strained from the tank at the same rate. Okay, so before going into the questions, let's uh, let's list what's given already. So the tank contains 40 kilogram of salt initially, so 40 kilogram will be Q0, right? So Q is the amount of salt, and Q0 is equal to 40 kilogram. And then the volume of the tank is equal to 600 liters, okay? And the solution containing 0.5 kilogram salt per liter. So per liter, kilogram per liter means kilogram divided by liter, right? So this is the unit, kilogram divided by liters, and this is 0.5. And what kind of information does this give us? This is dq/dv, because we have the amount divided by liters, right? So this is the amount in the liter. So this will be basically the density, right? dq/dv. Okay, so the volume derivative of the amount. Okay, and also here we have another information. It says the uh, the the solution enters the tank at a rate of 4 liters per minute. Okay, so we have 4 liters per minute. If we check the units, you'll see this is liter per minute, so this is kind of speed, right? How many liters will enter after 5 minutes? It will be 20 liters. Okay, it's like that. So dv in dt is basically the the speed of volume increase in the, or speed of entering volume is equal to 4 liters per minute. And it says it's also drained from the tank at the same rate, so the speed has to be same for the leaving solution. Okay, so dv out dt is still 4 liters per minute. Okay, these are all given, and it asks us about finding a differential equation for the quantity qt of the salt at time t greater than 0. Okay, and also we need to find the limit as t approaches infinity. Okay, so let's start with the first one. By the chain rule, dq in dt is basically equal to this, right? Because dq dt is equal to dq dv dt, right? Because if we have intermediate parameter, we can break the as like chain. We can use the chain rule and say the derivative with respect to the original parameter is equal to the derivative with respect to the intermediate parameter times the derivative of intermediate parameter with respect to the original parameter. Okay, so this is the chain rule, to remind you. And also the same goes for dq out dt. Okay, and this will be basically the same. If we substitute this in the Model's equation, by Model's equation I mean this equation here. Okay, so the equation we obtained after using conservation of mass. Okay, if we substitute this in the Model's equation, dq dt will be equal to dq in dv in times dv in dt minus dq out dv out dv out dt dv out dt. Okay, so this will be the new form for our model. Okay, so then if we substitute what's already known, dq in dv in, for example, dq in dv in is already given, so this is 0.5, so we put 0.5 here. Also dv in dt, the speed of the entering volume is 4, so it's given, so we substitute 4 here. Also dv out dt is known, and it's basically same as dv in dt because they are the same, so 4 comes here, and we left with this term here, dq out dv out, and on the left hand side we have dq dt remains. Okay, the rest of the terms are already given. Okay, so this has to be this we need to compare this with that and try to find something. We try to relate this dq out dv out with this q parameter, otherwise this problem is not solvable because we have two unknowns, right? Okay, so let's check our physical expectations. What is the density of, this is basically the density of the leaving solution. Okay, what is the density of the leaving solution? It's wet stirred tank, right? So the density of the leaving solution is basically equal to the density of the solution in the tank. Okay, so this is basically equal to dq out dv out, basically equal to the amount of salt in the tank divided by the volume of tank, right? Okay, qt over v tank. Okay, so this is the density, and we know qt is unknown, so we will leave it as is, and 600 is the volume of tank, and it's not changing because the speed of entering the solution and speed of leaving solutions are the same, so the volume will remain the same all the time, and this will be 600. Okay, and then we see dq dt is equal to, if we substitute this information in the equation here, in this equation, okay, then dq dt will be equal to 0.5 times 4 minus 4 times dq over 600, right? Because we know dq out dv out is equal to qt over 600. Okay, if we do some algebra, we'll get 2 here, and minus 4 times dq over 600 will be qt over 150. Okay, so this will be our differential equation. And then if we use the initial data, like the initial amount of the salt in the tank is 40 kilogram, this will be an initial value problem. Okay, so we need to solve this initial value problem. If you move this qt to the left hand side, we see this is an linear equation. Okay, so we basically solve the first order linear initial value problem. Okay, so this is linear because we have the time derivative of q, and also 1 over 150 times qt. This is some function of time times qt, the unknown, and basically 2 on the right hand side. Okay, so this is linear. Finding integrating factor, we see mu is equal to e to the t over 150. Okay, if we solve this linear differential equation, we will obtain basically this solution here. Okay, this is the solution. And then if we use the initial value and substitute 0 for time, this will be basically 1, and this will be 300 plus c. Okay, 300 plus c is equal to 40 because the initial amount is 40, so this will be 40. And then if we try to find c, this will be negative 260. Okay, so when we substitute c in the solution, okay, so in this solution we obtain qt is equal to 300 minus 260 e to the negative t over 150. Okay, next we investigate the behavior of the solution as time goes on and on. Okay, by this limit as t approaches infinity qt. Okay, so as t approaches infinity, qt will be 300 minus 260 e to the negative t over 150. And as t approaches infinity, this quantity will approach to 0. Okay, so this approaching 0 means we were left with 300. Okay, so 300. Then this limit is 300. Does it make sense? We need to check with the incoming solution. Okay, so if we have some solution in the tank, and if we let some incoming solution to come in and leave with some and let some solution to leave, then after some time we will see the density of the solution in the tank will be approaching to the same density of the incoming solution. Okay, if it's this incoming solution will be entering long enough. Okay, then we need to compare these results with the density of the incoming solution. Okay, the incoming solution contains 0.5 kilogram salt per liter, and the tank itself is 600 liters. Okay, then it means if the tank is filled with the incoming solution fully, then we will end up at 300 kilogram of salt. Okay, and this makes sense because after waiting long enough we obtain 300 kilogram salt in the tank already. So physically we find this solution to be a reasonable solution. Okay, so that makes sense. Thanks for watching. See you next time. Bye.